Okay, good morning. So today we'll discuss. In previous classes, I have discussed about Compton effect. I think you solved it. You have completed the assignment. In between, in the expansion of a plus b whole square, there we did not write one value. Okay, so that you can do it. Okay. So finally, how Compton shift varies with angle of scattering, because in angle of scattering, with the angle of scattering, the energy value varying, that is wavelength frequency of photon is varying. That what we have discussed. So now today we'll discuss matter waves and de-Broglie hypothesis. So what are matter waves? Matter waves are the waves associated with moving matter, moving electron, proton, neutron, not moving ball, cricket ball, football, or a cycle. So here matter in the sense almost fundamental particles. When an electron is moving with some velocity, that electron is associated with a wave. Okay, that wave is called matter wave. So the wave associated with moving matter is called matter wave. Clear? So this is very simple. I think it is easy to understand and even apply in application part. So this moving matter and its mathematical value and this concept is, it is a hypothesis given by de-Broglie, and after that, after a few years, Davison-Germer and G.P. Thomson this tried to prove it experimentally. Okay, so the hypothesis we'll discuss the de-Broglie hypothesis. So what de-Broglie, why the de-Broglie assumed it? Few things are there. One of the thing is uh, wave phenomena. If you consider wave traveling along a stretcher string, okay, that is a when you calculate fundamental frequencies, first harmonic, second harmonic, or overtones, when a wave is traveling along stretcher string, or you take closed or open tubes and different notes. If you take a flute, different notes are possible. So that frequency of those oscillations can be written as integer multiples of a fundamental frequency. Okay, so that value we generally we get uh, 1 by 12 root t by m. This is the value we get. That is fundamental frequency, first harmonic. Second harmonic we can write 2 by 12 root t by m. T tension in the string, m is the linear density. Similarly, 3, 4 into, so twice integer multiples 2 into n, n is 1 by 12 root of t by m. Similarly, 3n, 4n, like that we can write. So when a wave phenomena, if can be written as integral multiples of a fundamental value, any particular value, at the same time, comparatively, when electron is revolving in the orbits, its angular momentum also can be written as its integral multiples of that's nh by 2 pi, that value is there. So by comparing these two things, de Broglie assumed that, and one more important point also is there. One more important point is to explain few properties in optics, like Compton effect, photoelectric effect. There we don't consider wave nature of the electromagnetic radiation. There we take photon. Photon is a particle nature phenomenon, energy packet. So to explain certain things in optics, we are adopting particle nature for a wave natured electromagnetic radiation, generally electromagnetic wave. Okay, so same these two things made de-Broglie hypothesis think in different manner. So why not, when electron is moving with some velocity, why not it possess wave phenomena? When a wave is traveling, a wave phenomena thing is traveling, to explain some things, when we adopt a particle nature to that wave phenomena, why not a particle which is moving should possess wave nature or wave phenomena? So that's what the thing he got in his mind and worked out. So he gave a hypothesis, that is de-Broglie hypothesis, right? So initially he has taken a photon of energy h nu according to Planck's law. At the same time, if same energy, if you want to write in terms of velocity of light, then it can be written as mc square, Einstein relation. So from these, it is these two equations representing energy of single particle or single photon. So we can equate them. H nu equal to mc square. H nu is c by lambda. H c by lambda equal to mc square. H by lambda is equal to mc. So this is in case of photon. For example, a particle is moving with velocity v, then we can replace c with v. C is the velocity of light. Photon travels with velocity of light, right? So if a particle is moving, then we can replace c in that equation with v. So here now equation is becoming h by lambda is equal to m into v. M is the mass of the particle, v is the velocity with which it is moving, and h Planck's constant, and lambda is very important. So mass into velocity can be written as momentum p. Lambda is equal to h by p. The wavelength of the particle here, the wavelength of the wave, which is associated with moving matter of mass m, is h by p. This is what his hypothesis. So based on this, much theory is developed, and of course experimentally also that nature, that wave phenomena is observed, right? So say electron, let us take a particle, electron you can take. Let us take electron. The electron is moving with some velocity, or any particle is moving with some energy E, then the momentum, we can write the kinetic energy in terms of momentum. P square by 2m is equal to E. So momentum P is equal to root of 2me. So if depending on the known value, you can use the formula to calculate wavelength. So now wavelength becomes right? So let us calculate for electron. Simple thing. An electron is moving with velocity v. Um, how much kinetic energy it has can be calculated by applying a retarding potential. If you can stop it when it is moving with 100 kilojoules kinetic energy, say, then if you want to stop a electron which is moving with 100 kilojoules kinetic energy, how much retarding potential, how much opposite potential energy should be applied? Same. How much kinetic energy it has, that much potential energy you should apply. Okay. So the energy, kinetic energy of mv square, we are applying a retarding potential E into V, right? So this again we can write in terms of momentum. Momentum of the electron now becomes root of 2 m E into V. Therefore, therefore now the wavelength of the electron becomes h by root 2 m E into V. So actually here m is the relativistic mass. Okay. When electron is moving with some velocity v, then its relativistic mass becomes m naught, where m naught is its rest mass. Rest mass of electron is m naught. How much? 9.1 into 10 power minus 31 kilograms. M naught is the rest mass of the electron. 9.1 into 10 power minus 31 kilograms. So m is relativistic mass. Okay, according to relativity theory, the variation in mass takes place when it is moving with velocity v, almost which is near to c in that high speeds only. So anyway, in the calculations we don't consider this one. Approximately we make m is equal to m naught. In general, in general calculations, we take the relativistic mass as its rest mass of the electron. Approximate value we take. So in this formula, h is Planck's constant, m is the mass of the electron, E is charge of electron. How much? 1.6 into 10 power of minus 19 coulombs. Then if you apply and if you calculate, because h is constant, m is constant, E is constant. So lambda is depending only on V, how much potential we are applying. So if you calculate, you will get this 12.26 by root V angstroms. Clear? This is de-Broglie hypothesis of the electron, right? Now we'll discuss its experimental proof. Davison-Germer experiment. It's very, very interesting, very simple experiment. And okay, so in the Davison-Germer experiment, I will explain the experiment. What is the aim of the experiment? To prove or to verify, to prove the wave nature of moving matter, moving electron particularly. Okay, so for that we need fast moving electrons. How can we produce fast moving electrons? How to get? For that they take a tungsten filament, hot tungsten filament. When you heat it, then electrons will come out of the tungsten filament. Tungsten filament, from that electrons are emitted out. Okay, and many electrons will come out. So to make to get the collimated electron beam. That is a electron beam or stream of electrons in a single line. That is collimated electron beam. That is required. For that, we use a circular plate which has a small hole at its center. Okay, the circular plate, it has a small hole at its center, so that those electrons will enter into that hole, which are entered into that hole will travel further. To give more velocities, more kinetic energy to that emitted electrons, a potential difference is applied across plate and filament, so that emitted electrons will be accelerated further, because we need fast moving electrons to get better results. So these fast moving electrons are made to incident on a nickel surface. The scattered electrons will travel. See, the scattered electrons at the nickel surface, electrons will be get scattered at nickel surface with some angle. So we should have a system to capture them. Okay. So how they, uh, with what angle they will get scattered, we don't know. So whatever the angle these electrons get scattered, let whatever may be the angle, you should be in a position to capture that scattered electron. That is the thing, that is the phenomena here we have to develop. Accordingly, experimental setup will be there. So there they use a circular, moving on a circular path. That cylinder that moves with respect to the angle of scattering. Okay, so that collects the electrons, scattered electrons. So it is called collector, Faraday cylinder or collector. Okay, and that is the Faraday cylinder. Further, some when electrons are entered into it, in terms of flow of current, in the ammeter shows the deflection. We can measure intensity of the electron collected. Current itself, intensity of the electrons collected. Right. So these electrons are get scattered at these electrons get scattered at nickel surface within some angle theta, so that they are collected by Faraday cylinder. Here one more possibility is there. What is the possibilities? Because as we are producing fast moving electrons, as we are making to hit nickel surface, these fast moving electrons, as these fast moving electrons are made to hit nickel surface, at the nickel surface, the electrons at the surface of the nickel may get energy from that fast moving electron collision, and they may come out of the nickel surface. Right. So this fast moving electron hits the nickel surface. The electrons at that surface, nearer to the nickel surface, may absorb energy from this fast moving electron and may come out. Right. So if they possess very lower velocities, they may travel along the scattered electron direction. If they enter into the cylinder, we get the different values of intensity. So our experimental main motto may change, right? So we should stop those secondary electrons. Okay, there the secondary electrons emitted should not travel, should not enter into Faraday cylinder. Further, across the cylinder faces, opposite faces, a retarding potential is applied. Across that, some potential difference, a negative potential difference we maintain. How much we maintain is which can stop only secondary electrons but not primary electron. Primary electron is what? The primary electrons are the electrons emitted at the tungsten filament traveling with higher speeds and get scattered. Those are primary electrons. Whatever the retarding potential we applied there should not stopping potential, should not stop these primary electrons. Okay, that value should stop only these secondary electrons. Anyway, the energy of the secondary electrons is very less than that of the primary electrons. So, according to the energy of the secondary electrons, you can apply retarding potential here, negative potential, so that they will be stopped. This is a simple phenomenon. So, as the theta varies, the function of theta, the Faraday cylinder moves and collects the electrons. Clear? This is experimental setup of the Davison-Germer experiment. Again, let me repeat once. Listen, if anybody did not concentrate. We take a hot tungsten filament. From that, electrons will be emitted out in many different directions. We need a straight collimated beam, stream of electrons in a particular direction. So we are stopping remaining electrons at the circular plate by making a small hole at its center. The electrons which are entered into that small hole will travel further. To accelerate them, because we need higher kinetic energy electrons. So to accelerate them, we are applying a potential here. Accelerating potential we are applying. So that electrons are accelerated and hits on nickel surface. The electrons which are hit nickel surface get scatters with an angle theta and are collected by Faraday cylinder. Right, Faraday cylinder is a rotatable cylinder, rotates with the function of this angle of scattering. One more thing we did is to stop the secondary electrons emitted at nickel surface, we applied a negative potential, stopping potential across the opposite faces of the Faraday cylinder, and that energy is just up to the energy of the secondary electrons. That energy stops only secondary electrons but not primary electrons, right? Okay, that is construction. Okay, now we'll see from this the data what they got. Davison-Germer, they analyzed it. They applied de-Broglie hypothesis and also they applied Bragg's law. Bragg's law is just, it is the X-ray diffraction is explained by Bragg's law. That is, it is explained, it is applied for waves hitting a crystal surface or get diffracted. Okay, the Bragg's law is applied, uh, developed to understand the crystal structure. To understand the crystal structure, some light X-rays are made to incident on that, and the diffracted rays are observed by seeing the spectrum, by analyzing it, what type of order we are getting, like that. By analyzing it, they try to analyze the crystal structure. They try to understand the crystal structure. Okay, here we know crystal, nickel crystal we know, and also we know its interplanar spacing 0.909 into 10 power minus 10, 0.909 um, interplanar spacing, the space between the planes in the nickel crystal. Okay, we'll draw the diagram. Okay, these are the planes in the nickel crystal. This is the electron hits a atom on the nickel surface and scatters with the 50 degrees angle. Okay, this is the experimental value. They applied some voltage, 54 volts. Then they seen a 50 degrees angle of scattering. Okay, now they apply de-Broglie hypothesis here. So here 50 degrees in the sense, we need to apply the de-Broglie hypothesis. We need this angle. How much it will be? If it is 50, 25, 25, this is 90, this is 65. Right. So according to Bragg's law, 2d sine theta is equal to n lambda. Right. So what is d value to interplanar spacing? Here d interplanar spacing in the nickel crystal surface for that what they observed, which planes they have taken for that plane. The interplanar spacing is 0.90 into 10 power minus 10, 2 into d sine theta. Sine theta is and Bragg's angle, theta dash, we can call theta dash. In Bragg, okay, right. So in Bragg's law, theta dash angle is we are taking no that angle. So this value they obtained as 1.648 angstroms. Right. This value they obtained by applying angle of Bragg's law. Bragg's law is specifically designed to analyze wave to when you use waves. In that case, they to study the diffraction phenomena, they designed it. They developed that formula. Okay. Now we'll apply de-Broglie hypothesis. Okay. Here I will write. According to de-Broglie hypothesis, the formula is 2.26 by root V angstroms. How much V? We applied 54 degrees. So 12.26 by root V. Approximately they got 1.65. Approximately they got 1.658 angstroms. By applying de Broglie wavelength phenomena, de Broglie hypothesis, this is the wavelength of the moving matter associated with electrons. By applying this lambda, they got, by applying this formula, the lambda value they got 1.658 angstroms. Whereas in Bragg's law, they got 1.648 angstroms. See, the values are very much nearer, almost same. So by seeing this value, they concluded the moving matter may associate with wave nature. So here electrons are hitting, but according to this, we should not say electrons are hitting. Of course, electron. The wave associated with electron hits the nickel surface and gets scattered. The which is gets scattered there? Which one? The wave which is associated with moving matter. In that way we can say. So it is experimental proof. They have The thing is, stationery shops also not in open. So I need to optimize the place. Okay, because if I want to get these sheets, I'm not able to get here. 3 more sheets are there. We should run it. 3 more sheets in the sense, one side one class, another side another class. 6 classes maximum. So after 7, okay. So anyway, if graph is drawn between angle of scattering and intensity of light, intensity of electrons received at Faraday cylinder, that is current itself. Then, very interestingly, graph is seen like this. See, with the variation of theta for different angle of scatterings, the intensity of the electrons received at Faraday cylinder is varying like this. Okay, so this is the phenomena of diffraction. If you see the diffraction of electromagnetic radiation, they're also same here, intensity and K value. Same, see half part of it. There you see. Okay, this is diffraction pattern drawn in case of electromagnetic waves diffraction. When optical signals are get diffracted, this is the thing observed. This is the number of electrons collected at Faraday cylinder to the angle of scattering it is drawn. See the similarity of the graphs. So from these two conclusions, from these two experimental proofs, Davison and Germer finally decided, confirmed it. The moving matter is associated with wave nature. Okay. Similarly, G.P. Thomson experiment also is there. There also it is proved. We don't have in syllabus. We'll see whenever we find time. We'll discuss. That is also very interesting. G.P. Thomson. Okay. Clear? So if you have any doubts, you can ask. This is the topic today. Tomorrow we will discuss Schrodinger wave equation, particle in a box, right? Or Schrodinger wave equation, significance of wave function. For particle in a box, we need one big sheet. So Schrodinger wave equation and significance of wave function. And also, if possible, if time permits, we'll discuss uncertainty principle also. Okay. So that is class for today. Again, do yoga. I shared a link with you. Do the yoga. I think some of you are practicing it. See it. Okay. Today in the today live class, they have shown Surya Namaskaras. Very, very important. To be mentally and physically to be healthy, practice yoga, read books. And today I have seen in paper, without examinations, we don't want to give any degree or any certificate. That is the his chairman or the person mentioned today. I read in paper. So people, you all of you, be ready for examinations. Prepare. I think you are preparing, but make prepare seriously. Okay, practice. Just read it, write it till you get clarity. Okay. ఇంట్లోనే ఉండండి, జాగ్రత్తగా ఉండండి, హ్యాపీగా ఉండండి, బాగా చదువుకోండి. Okay, again we'll continue tomorrow. Good day.